Welcome to today's deep dive, everyone. I'm your host, and as always, I've got our resident expert here with me to help break down some pretty wild technology.
Hey everyone. Yeah, I'm really excited for this one. It's definitely a fascinating topic today.
It really is. So for you listening, I want you to imagine something. Imagine walking through a massive, high-pressure chemical plant.
Like a really complex, dangerous environment.
Exactly. And you're just snapping a few random photos with your smartphone as you walk around.
Just, normal phone pictures.
Right. And somehow, by doing just that, you accidentally generate a live operating digital replica of the entire facility.
It sounds completely like science fiction.
It really does. But today, we are looking at the actual architecture that makes this a reality.
Yeah, it's happening right now.
Right. And usually when we talk about a blueprint or like a schematic, there's this expectation of total certainty,
Oh, absolutely.
Think about following the instructions to build a piece of flat pack furniture. The drawing says part A goes into slot B. So you look in the box and there's part A.
Exactly as drawn.
Exactly. Ready to slide right into slot B. You expect the map to just be a perfect representation of the territory.
It is comforting to have that clean binary reality. We all like things to just work.
Oh, for sure.
The problem is that when you step into the world of complex industrial engineering, so massive chemical plants, oil refineries, intricate manufacturing facilities, that perfect blueprint is usually missing half the story.
Right.
The informational landscape in these environments is completely fractured. You have the theory of what the plant should be living in one database somewhere.
In a perfect world.
Right. And then you have the messy, sprawling reality of what is actually sitting there in the physical world.
Which might have been modified, dozens of times over 20 years?
Exactly. And bridging that gap has historically been an incredibly slow, highly manual, and frankly, extremely expensive process.
Yeah.
It is the absolute definition of an engineering blind spot.
Which is why today's source material is so compelling.
Yeah. The people.
We are exploring a July 8, 2026 press release, along with the accompanying technical architecture from a company called EON AI Ventures.
Right.
And they're detailing a platform called EON Universal. Their central claim is that a stack of ordinary smartphone photos can be instantly transformed not just into a static 3D model, but into a live running digital twin of a complex industrial facility.
Which is a massive leap.
Okay, let's unpack this, because if I'm understanding the core premise here, we are talking about a massive paradigm-shifting difference between just looking at a digital picture of a plant and actually operating it.
To grasp the magnitude of what EON AI Ventures has accomplished, we really have to start by defining that engineering blind spot a bit more clearly. It is essentially a tale of two very different types of data that just refuse to talk to each other. On one side, you have the P&ID.
Which is?
That stands for Piping and Instrumentation Diagram. This is basically the engineer's holy grail.
Because it's the blueprint.
Right, because it captures connectivity and identity perfectly. It dictates that valve 402 must connect to pump 7 via a very specific type of high-pressure pipe.
So it's the absolute logical truth of the facility's design.
Exactly. The catch is that it has absolutely no geometry.
Wait, no geometry at all?
None. The P&ID does not tell you if valve 402 is 3 feet away from the pump or, 3 stories up on a scaffolding on the complete other side of the building.
Wow.
Yeah, it is all logic, zero physical reality.
Okay, and a point cloud is kind of the exact inverse of that.
Completely the opposite.
For you listening, a photogrammetric point cloud is what you get when you laser scan a facility, or when you use drones to take thousands of pictures to build a really highly accurate 3D model.
And they look amazing.
They do. Visually, they capture geometry perfectly. They map every inch of the physical space. But a point cloud has absolutely zero meaning.
Right.
To a laser scanner, a critical high-pressure safety valve, and like a random coffee cup left on a railing by a worker, they're indistinguishable.
The shapes.
Right. They're both just a cluster of digital dots in space. The software doesn't know what anything actually is.
And that fundamental disconnect is what leaves facility operators stranded. You have the logic without the shape on one hand and the shape without the logic on the other.
I'm trying to visualize this for you, the listener. It feels like having two completely useless maps of a city.
That's a good way to put it.
Like, the point cloud is essentially a highly detailed satellite photo of a sprawling metropolis, but there are no labels.
You see buildings, but you don't know what they do.
Exactly. You can't tell the hospital from the grocery store.
Yeah.
Meanwhile, the P&ID, the engineering diagram, is like a giant phone book with
Yeah.
all the names and numbers of every business in that city, but no addresses.
Yes. You have the mapeless directory, and you have the blind map. EON Universal's entire mission is to fuse those two things together.
Which sounds incredibly difficult.
What's fascinating here is how they do it. This is not some simple data mashup where you just overlay the text onto the 3D shapes and cross your fingers.
Right, hoping it just snaps together.
They use an architecture built around an orchestration layer. This requires the system to mathematically and logically prove the connection between the physical shape and the engineering logic before it builds the model.
That concept of an orchestration layer is interesting, but I have to challenge this premise right out of the gate.
Okay, let's hear it.
If we are fusing two completely different types of data, the phone book and the satellite map, how do we prevent the system from creating a messy, inaccurate hybrid?
Well, that's the big risk, right?
Because AI is notorious for hallucinating. We've all seen AI generate images with missing fingers or confidently invent fake historical facts.
Oh yeah, all the time.
So if I am running a high-pressure chemical plant, I cannot have my 3D model just guessing where a safety valve is because the lighting was bad in a photograph.
Absolutely not.
How can we possibly trust an AI system with critical infrastructure?
EON Universal anticipates that exact skepticism. The orchestration layer does not blindly trust the AI. You can think of the orchestrator as a single master controller that sequences the work.
Okay, so it's not just one big AI doing everything.
No, it doesn't process data in one big gulp. Instead, it dispatches what they call purpose-built agents to handle very specific subtasks.
Like specialists.
Think of these agents like specialized contractors on a job site. The orchestrator says, I need to read the text off that dirty valve tag, and it sends a specialized vision language agent.
I see.
Then it says, I need to calculate the diameter of this pipe, and it sends a geometric analysis agent right after.
So it's breaking the massive problem down into tiny, highly specialized microtasks.
It goes deeper than that.
Huh.
To prevent the hallucinations you mentioned, the orchestrator employs a central verification discipline.
A verification discipline. What does that look like?
It acts as an adversarial bouncer standing at the door of the digital twin. This bouncer operates on one strict, unbreakable golden rule.
Which is?
Absolutely no fact enters the digital twin until independent sources agree. The AI analyzing the photographs and the logic extracted from the PNID drawing must independently arrive at the exact same conclusion.
Oh, wow.
Yeah, the system is running per-part checks in parallel, explicitly cross-referencing its findings before letting anything through the door.
So what happens when they don't agree? Say the AI agent looks at a photo and sees what clearly looks like a valve, but the PNID diagram insists there should only be a straight pipe in that location.
That's a great question.
Does the AI just override the old drawing?
Never. If there is a conflict, the system refuses to silently overwrite the data to make it fit. Conflicts are immediately recorded and explicitly flagged for a human engineer to review.
Okay, so it defers to a person.
Exactly. The integrity of the engineering data is protected at all costs. The system actually re-inspects the full resolution source image before it trusts any AI verdict.
Right.
And if it still can't reconcile the visual reality with the engineering logic, it halts and asks for human intervention.
That makes a lot of sense. The bouncer at the door is incredibly strict, which builds the trust.
Exactly.
But a bouncer is useless if no one is trying to get in the door. How is the system actually generating the 3D shapes to submit for this verification in the first place?
Right. How do we get the shapes?
That brings us to the first major stage of their pipeline, which EON calls recognition.
Recognition is the process of understanding what the parts are and where they sit in 3D space. It produces three distinct deliverables: the skeleton, the crops, and the scale.
Okay, let's start with the skeleton.
Starting with the skeleton, the system has to completely rebuild the 3D structure from flat 2D smartphone photos. They achieve this using a technique called structure from motion.
I've heard of that.
Yeah, specifically relying on frameworks like ColMap and PyColMap.
So structure from motion is essentially the software looking at how the perspective of an object shifts as you move a camera around it, right?
Yes.
Similar to how your two eyes give you depth perception, but scaled up to dozens of camera angles.
Yeah.
But the technical details in the source show how granular this gets. The system analyzes roughly 3,700 SIFT features per photo.
SIF stands for Scale Invariant Feature Transform. In plain English, the algorithm scans a photo and finds thousands of unique microscopic anchor points.
What kind of points?
It might be the exact jagged corner of a rust spot or a tiny specific scratch on a painted pipe. The brilliance of a SIFT feature is that it mathematically describes that tiny detail in a way that looks the same to the computer, regardless of what angle or distance the camera is viewing it from.
So even if I'm standing far away or up close, it knows it's the exact same scratch.
Yes. Once it identifies these thousands of microscopic anchors across dozens of photos, it uses exhaustive matching and a process called global bundle adjustment.
How does global bundle adjustment actually map the space? Because just matching a scratch on a pipe in two photos doesn't really tell you the 3D dimensions of the room.
Think of it as drawing invisible laser lines.
Okay.
The algorithm draws a line from the tiny scratch on the pipe back to the camera lens in photo 1. Then it does the same for photo 2.
Right.
By calculating the intersecting angles of millions of these invisible lines simultaneously, it's solving a massive mathematical optimization puzzle. It figures out exactly where every single rust spot and scratch is in 3D space,
That's incredible.
while simultaneously calculating the exact XYZ coordinates of where the photographer's feet were planted when they took each picture.
And it uses the EXIF data, right? Like the metadata embedded in the photo by the smartphone's camera things like focal length and sensor size to refine those angles.
It does, and there is also a vital rule built into this step. The system completely excludes near-duplicate camera angles, specifically any photos taken with under a 5-degree baseline shift.
Oh, that makes sense. That forces the photographer to actually move around.
Exactly.
If someone just stands in one spot and fires off 20 photos without moving their feet, they aren't providing new 3D information.
Right, they're just artificially inflating the software's confidence with redundant data.
So by tossing out those redundant angles, the system stays honest and demands true multi-angle perspective.
Once that 3D skeleton of points is built, the system transitions to the second deliverable of the recognition stage, the crops.
Because building the shape is only half the battle.
Right. The system still has to figure out what those shapes represent. When the orchestrator encounters a part it is uncertain about, it literally cuts it out. It crops it from the full resolution image data.
Okay.
It isolates the object and examines it from about 14 different angles.
It's the digital equivalent of an inspector walking circles around a piece of equipment, just squinting at it from every conceivable side before deciding what it is.
And this is where that adversarial bouncer steps back in. The part is only marked as verified if the visual imagery clears a remarkably high confidence bar across at least 2 completely different viewing angles.
2 different angles.
And that visual confirmation must perfectly match the engineering tag from the PNID.
Here's where it gets really interesting.
Yeah.
Because this multi-angle discipline is so rigorous, so stubbornly thorough, that it creates unexpected outcomes in the field.
Yeah, this part is great.
The source notes that this process not only corrects mislabels, but it actively rejects parts that turn out to be humans.
That's right.
Like if an operator accidentally wanders into the frame while the photos are being taken, the AI might initially look at one photo and say, what is this unknown cylinder-shaped object blocking the pipe?
Right.
But after attempting to check it from 13 different angles across various photos, it realizes the object moved or just disappeared. It concludes, oh, that's just Steve from maintenance, and it entirely rejects the anomaly from the twin.
It is a perfect demonstration of how robust the verification really is. The system refuses to be fooled by transient objects, shadows, or reflections because it relies on persistent multi-angle consensus.
Makes total sense.
Which leads directly to the third, and perhaps most difficult, deliverable of the recognition stage.
Scale.
Because structure for motion is incredibly good at getting the shape right, but it is entirely scale-free.
Totally scale-free.
The algorithm builds a perfect 3D model, but it has no internal ruler. It has absolutely no idea if the model it just generated is 20 feet tall or 2 inches tall.
Right, it understands the proportions perfectly, but not the absolute real-world measurements.
This reminds me of those incredible photos NASA gets back from the Mars rovers. You see a high-resolution, close-up photo of a rock on the Martian surface.
Yeah.
But because there is no atmosphere to provide depth haze, and absolutely no familiar objects in the frame like a tree or a shoe, your brain has zero context for scale.
You're just guessing.
Is that rock the size of a pebble, or is it the size of a minivan? You literally have no idea until the rover drives forward and you see a piece of the rover's metal wheel next to it for context. You need an anchor. That is a brilliant comparison. EON Universal has to find its rover wheels. It has to hunt for anchors in the photos to lock the digital twin into real-world metric scale.
Okay.
They approach this using a methodology called multi-anchor consensus, pulling these anchors from several clever sources.
Where do they find these contextual clues in a random pump room?
Well, first, the system utilizes known component dimensions from their smart 3D library. If the visual AI recognizes a very specific branded valve, the library database already knows the exact physical dimensions of that valve.
Smart.
Second, it consults the P&ID diagram to look at the designated line size, which implies standard outer diameters for the pipes and flanges in the photos.
Okay, that's two.
Third, the vision agents can actually read branded catalog nameplates bolted onto the machinery.
Oh, wow.
And finally, if the environment is completely devoid of standard parts, a worker can just drop a tape measure into the scene before taking the photos.
So it's pulling scale clues from every possible angle. But again, it doesn't just blindly trust the first anchor it finds.
Yeah. Never. The system requires at least two independent anchors before it commits to a scale, and there is an intense layer of statistical rigor applied here.
Okay.
Each anchor the system finds implies a certain overall scale for the entire scene. The software gathers all those implied scales and takes the median value, not the average.
Okay, explain the mathematical logic behind using the median instead of the average there. Why does that matter?
Because averages are easily destroyed by extreme outliers.
Give me an example.
Imagine the system finds 5 anchors for scale. 4 of those anchors suggest the pipe is about 2 inches wide, but the 5th anchor is a hallucination. Maybe the AI misread a shadow as a massive structural beam,
Right.
and it suggests the pipe is 50 feet wide. If you average those 5 numbers together, the entire 3D model gets scaled up to an absurd, unusable size.
The one bad data point drags the entire average completely off reality.
Precisely. But the median simply lines all the values up in order and picks the one exactly in the middle. It completely nullifies the extreme 50-foot outlier.
That's so elegant.
And the system then reports the spread as a mathematical error bar and actively flags that outlier for a human to investigate, rather than just silently blending it into an average. It is engineering-grade precision applied to photography.
Theory and statistics are great, but the source material actually provides the results of a real-world test. Because the true test of this architecture is what happens when someone walks around a real messy facility with a standard smartphone.
The field validation results provided by EON AI Ventures are incredibly telling. They tested this on a live equipment skid.
Which is like a modular frame containing complex piping, valves, and instruments.
Exactly.
The numbers in the report are wild. They took just 54 handheld phone photos of this skid. The system successfully placed 32 of those photos into a single continuous 3D frame.
Yep.
And the mean reprojection error, which is basically a measurement of how far off a calculated 3D point is when you mathematically project it back onto the original 2D photo, was just 0.49 pixels.
That's high.
Less than half a pixel of error from someone just walking around with a phone.
It is astonishing accuracy, but the orchestration layer's verification pass is where the real value was proven. During that automated check, the system raised the number of confirmed verified parts from 5 up to 14.
Wow.
It caught and corrected a mislabeled part where the physical tag didn't match the engineering drawing. It flagged 4 distinct conflicts for human review.
And, as we discussed, it successfully rejected 2 people who had wandered into the frame during the photo capture.
Right, it proved the concept in the real world.
But this brings us to the biggest promise of the deep dive today. Having a highly accurate, verified, geometrically perfect 3D model is still just a picture.
It's a great picture, but it's not a live digital twin.
Exactly. How does this static 3D shape actually become a living, operating plant?
That metamorphosis happens in the final and most critical stage of the pipeline, configuration. Up until this point, the system has basically built a highly accurate shell. The orchestrator doesn't just leave the point cloud as a bunch of colorful dots. It physically rebuilds the facility in the digital space by swapping out the hollow shapes for intelligent CAD-grade components from its smart 3D library.
It swaps them out.
Yes, it drops correctly scaled, functional digital valves and pumps into the reconstructed frame, and then it automatically routes the digital pipework between them to connect everything perfectly, according to the logic of the P&ID.
So it's essentially replacing the dummy geometry with smart building blocks.
If we connect this to the bigger picture, these are no longer inert shapes. Every object drawn from that smart 3D library carries heavy engineering attributes.
Like what?
Well, the digital valve knows its own design pressure, its temperature ratings, its maintenance schedule, and its connection semantics.
Okay.
And because it possesses that internal logic, it can finally be bound to the live telemetry coming from the actual physical facility.
Walk us through how that telemetry binding actually works in practice.
Well,
How does the digital valve know what the physical valve is doing?
The PID doesn't just provide the logic of what connects to what. It also holds the data stream IDs, or IP addresses, for the digital sensors installed on the physical equipment.
oh, I see.
Because EON Universal has verified that the physical pump 7 in the photo is exactly the same as pump 7 in the PNID, it assigns the live data stream ID directly to the newly placed 3D CAD model.
So suddenly, the real-world RPMs of the physical pump are animating the digital pump on the screen in real time.
Exactly.
So imagine an operator sitting at a screen miles away from the actual plant. They aren't just looking at a 3D map. If a seal on a physical valve starts to fail and the pressure drops, that data flows instantly into the digital twin.
Instantly.
The operator can literally see the digital pipe change color to indicate a pressure anomaly. They can click on the digital valve, see the real-time flow rate, cross-reference it immediately with the manufacturer's design pressure, and diagnose the problem before catastrophic failure occurs. They're actually interrogating the model.
They are running the plant from within the twin. The visual model has become a massive interactive instrument dashboard.
There is a quote in the press release from Dan Lajerskar, the founder and chairman of EON AI Ventures, that sums this transition up perfectly. He states, "Everyone can make a point cloud. The hard part is making the twin true and then making it live. We fix the data first. Nothing enters the model until the photos and the drawing agree. Once the intelligent objects are in place and bound to telemetry, our customers aren't looking at a picture of their plant. They're running it."
That's a great quote. It represents a fundamental shift in industrial asset management.
Yeah.
And this deep focus on operability makes perfect sense when you look at the background of EON AI Ventures. They are not a new startup just playing with 3D rendering. They have a 25-year foundation in immersive learning technology deployed across more than 80 countries.
Boy.
This new EON Universal platform is designed to feed directly into their broader work intelligence platform, which includes tools like Genesis, Field IQ, and Assess IQ. Their overarching goal is capturing, verifying, and compounding the knowledge of how expert work is actually done in the field, and making that knowledge instantly accessible and actionable.
So what does this all mean for you, the listener? We are talking about a massive paradigm-shifting leap in how humanity interacts with the physical infrastructure of our world.
It's huge.
We're moving away from relying on static, blind diagrams that just sit in a filing cabinet gathering dust, or pretty 3D models that have absolutely no brain.
Right.
By applying ruthless verification and intelligent orchestration, we can take a few ordinary photos with a device we all carry in our pockets and instantly generate a living, breathing instrument of an industrial facility. It takes the absolute chaos of the physical world and maps it perfectly to the clean logic of the digital world, creating a unified source of truth.
It completely eliminates the gap between the map and the territory.
Exactly. Now, I want to leave you with a final thought to mull over, kind of building on the implications of what we've unpacked today.
Yeah, let's hear it.
If EON Universal can build a fully operable, highly verified digital twin of a complex, high-pressure industrial plant just from a stack of casual smartphone photos, what happens when this exact technology inevitably scales down to our personal lives?
Oh, that's an interesting thought.
Imagine taking your phone, walking a quick lap around your own house, and instantly generating a live digital twin of your home's entirely hidden infrastructure.
Wow.
We're talking about the electrical grid behind the drywall, the plumbing running under the floors, the HVAC systems in the ceiling. Could we all very soon become the facility operators of our own homes?
That would be amazing.
Imagine opening an app and diagnosing a hidden, slow water leak behind your bathroom mirror, or predicting an electrical short on your phone before it even sparks. The blueprint of the future isn't just a flat piece of paper showing you where things go. It's a live dashboard telling you exactly how your world is running.
It really is.
It's a fascinating future to look forward to. Thanks for joining us today, and we'll catch you on the next deep dive.